Very good. All right, thank you for the opportunity to speak here today. Today I'll be talking about some potential high priority science targets that we'll encounter during the ARTEMIS program. So ARTEMIS is relevant to a wide range of science goals. I'm going to focus today specifically on Report Goal 1B from the ARTEMIS 3 Science Definition Team report. So we want to probe planetary differentiation and evolution processes, including formation of a magma ocean, crust, mantle, and core. So that's pretty broad. Today I'm going to focus on one very specific goal, or one very specific question, which is, are we going to be able to sample material excavated by the South Pole Aitken Basin as part of the ARTEMIS program? So this is something we've been working on for several years, and we kind of have a series of papers that start to lay the case for this. So back in 2021, we published a paper looking at the compositional characteristics of possible SPA ejecta. We drew on lunar magma ocean models, and we focused on a few compositional markers of late-stage lunar magma ocean cumulates. So we have things like creep. We're mapping out the distribution of creep. Oh, sorry. Here, this is the distribution of thorium around SPA, recorded by Lunar Prospector. And we compared that to models of SPA formation. So this is the result of a three-dimensional impact model run by Jordan Kendall. And this black to red gradient shows the thickness of mantle-derived ejecta emplaced by the South Pole Aitken forming impact. And what you can see is that the distribution of this mantle ejecta convolved with 4 billion years of subsequent impact looks an awful lot like the current day distribution of creep and thorium and these other compositional markers we see on the surface of the moon today. So some of the specific compositional markers we were looking at are thorium, iron, and then the minerals we're seeing are really iron and calcium-rich pyroxenes, which are pretty different from the pyroxenes we see in the rest of SPA. And we'll go into that a little bit more as we go forward. So do we see any of these compositional markers across the ARTEMIS exploration zone? So this is a map of iron abundance on the left and thorium abundance on the right. These are both from Lunar Prospector. And the context of this map, the far side is to the bottom, the near side of the moon is to the top, and South Pole Aitken is down in this direction. And as you can see, there is this gradient in both iron and thorium abundance across the ARTEMIS exploration zone, suggesting that some of the candidate regions to the bottom left of this map, so this is the Diggerlash-Kosher Massif, this might be our best opportunity to sample SPA ejecta in this list of 13 candidate ARTEMIS 3 landing regions. But one issue is that Lunar Prospector data is really low spatial resolution. And there's a chance that this is just kind of a residual effect from elevated abundances in the SPA interior. So to confirm what we're seeing here in the Lunar Prospector, we turn to spectroscopy data. And this is stuff we present in a paper that just came out about a month or two ago. So on the left, we're showing a map of MAFIC abundance from Moon Mineralogy Mapper. This is a global mosaic with about 1 kilometer per pixel resolution. On the right is a map of iron abundance derived from Kaguya spectral profiler data that also has about a 1 kilometer per pixel resolution. And what we see is that both iron and mafic abundance are enriched in the direction of South Pole Aitken. And this now agrees between 3 different instruments. So we have Lunar Prospector, we have Moon Mineralogy Mapper, and we have Kaguya Spectral Profiler, showing that there is essentially an elevated amount of South Pole Aitken ejecta as you move across the ARTEMIS exploration zone towards the Diggerlash-Kosher Massif. One issue, which shows up pretty clearly in the Kaguya data, is that the Massif itself actually looks to be kind of a local minimum in iron abundance. So even though the overall distribution of iron and thorium is high in the region, on the Massif itself, it might be kind of low. But again, this is fairly low spatial resolution data. So next what we want to do is look at full resolution M-cube data. M-cubed is in a pole crossing orbit, so it collected a lot of data for the Artemis 3 candidate landing regions. So for the de Gerlache-Kosher Massif, we have 28 independent M-cubed images of that region at about 100 to 200 meters per pixel. And so what does that look like? So this is a map of topography for the de Gerlache-Kosher Massif on the left, and on the right is an M-cubed spectral parameter that's sensitive to mafic abundance, the abundance of mafic minerals. And so what we see is that there are two types of mafic anomalies going on here in this M-cubed image. So in the red arrows, I've indicated two small fresh impact craters. These are both about 300 meters in size. And in LRO NAC data, you can see that they are fresh, kind of rocky craters. The other mafic abundance anomalies we see here are associated with sun-facing slopes. So we want to investigate that a little further with actual spectra. But first, I just wanted to compare this full resolution M-cubed image to what we're seeing in the Kaguya. So you can see that the M-cubed offers a much higher spatial resolution than these Kaguya products. So at the moment, this offers our best combined spatial and spectral resolution for the South Pole. And these are two more NAC images of those 300-meter impact craters. When we extract spectra from the small craters shown in darker purple and the illuminated slope shown in the light purple, we see that they both indicate the presence of pyroxenes, given the absorption bands at 1 and 2 micron, but these are a little bit different. So there are different spectral characteristics here that we want to investigate. And specifically what we want to do is look at the positions, the central positions of these absorption bands. Pyroxenes have a very systematic trend or relationship between the 1 micron and 2 micron band center. So to confirm that these are kind of typical pyroxenes, we want to compare those band centers.
3 minutes.
Perfect. And so when we extract the band centers, we see that the band centers for the two small fresh craters fall right along this trend that you'd expect for pyroxene-bearing minerals or materials. They actually fall within this magnesium-rich pyroxene zone. That's in contrast to some of the thorium-bearing or thorium-rich materials we see in Northwest SPA that we associate with the lunar magma ocean drag ejecta. But another interesting point is that the sun-facing slopes, they did show this mafic anomaly in the spectral parameter, but they're way off the pyroxene trend. So something really unusual is going on here. This could be some kind of photometric artifact or something else. One thing that could give you these funky band centers is the presence of hematite, which Shuai Li explored the possibility of in a paper a few years ago. And he also saw that those are on kind of Earth-facing slopes. So it could be that these are indicating the presence of a lot of hematite as opposed to just pyroxene. But yeah, so to conclude, so ARTEMIS will be sampling diverse crustal materials in basin ejecta. But the main takeaway from this talk is that M-cubed is capable of identifying small-scale mafic anomalies, such as small fresh impact craters. And some of these craters identified near the de Gerlache-Kosher Massif, they exhibit a low calcium pyroxene composition, and they're not mineralogically similar to the thorium-bearing materials that we see in Northwest SPA that could represent LMO drag ejecta. And just as a bonus, I've been running a few traverses out to these small craters from a landing site of optimal illumination. So we're running least cost path models, incorporating topographic slope, direct to earth visibility, and average solar illumination. That gives us total traverses with lengths of about 10 to 20 kilometers. So not something we could really explore in ARTEMIS 3 or 4, but maybe beyond. When we have longer traverse capabilities, we'll be able to grab some of those.
30 seconds.
Then we're done. Thank you very much.